Here I'm standing with a group of fellow attendees of 2019's International Workshop on Adaptive, Compressive, and Computational Imaging at the Parnal Observatory of the European Southern Observatory in the Atacama Desert of Chile. We're standing in front of the VLT, the Very Large Telescope Array that the ESO runs there. These telescopes are connected interferometrically, so they can measure coherence functions exactly as we've discussed in this chapter. But that's not the topic of today's discussion. Today we want to talk about this use of the European Southern Observatory. Here, this of course is a fantastically beautiful image. We have the Milky Way right on a diagonal behind the observatory, and off to the left we have the large and small Magellan clouds. But coming out of the observatory, we have a laser guide star. And the guide star is used to characterize the atmosphere for adaptive optics to allow the telescope to see through turbulence. Today, we're going to talk about methods for achieving that goal. Computational imaging. Episode 47, Imaging Through Turbulence. Back in episode 34, we discussed how to image through inhomogeneous media with coherent fields. This example was imaging through a multimode fiber by characterizing the transmission matrix through the fiber and then inverting it with a neural estimator. For the coherent system, you just measure the field at the output, and knowing the transmission matrix, that will be sufficient to invert and recover the input field. For a partially coherent or incoherent system, one would need to fully characterize the coherence functions at the output of the inhomogeneous media, in addition to knowing the transmission matrix. So that would be a substantially more challenging problem. More often, one is interested in imaging through relatively small or simple inhomogeneities, such as the distortion due to the atmosphere. So as was shown in the introduction, you can either create or find a reference star in the system, and then if you assume that the turbulence is sufficiently weak that it acts simply as a pupil function and what's called an isoplanatic modulation, then you can image with a complementary pupil function to reverse the turbulence and form a well-formed image. So this is the basis of adaptive optical systems that are used in telescopes. One uses a guide star to characterize the effective exit pupil of the system with the perturbation due to the turbulence, and then one uses adaptive optics to correct for it. To measure the distortion due to the turbulence, find the exit pupil basically, one uses wavefront sensors. And so here at the lower left you see a Shack-Hartman sensor, which uses a micro lens array to find the local tilt. This is assuming very weak modulation of the pupil function, so that the distortion would just have a simple wavefront tilt on the scale of several pixels. If there's more severe distortion, you could use a wavefront camera, such as the wavefront cameras that we discussed in episode 40, or you could use holographic techniques to characterize an extreme distortion to the wavefront. Of course, in that case, one would find that the isoplanatic assumption is also most likely violated. So that's the basis of adaptive optics. Characterize the effective exit pupil, compensate for it, and form a well-formed image. That's based on imaging analysis for the pupil function and incoherent systems that we're going to discuss in the next chapter, chapter 8. Today we want to wrap up our discussion of coherent sensing by pointing out that these systems with some distortion can be compensated by coherence measures, such as we've discussed in this chapter. For example, this paper looked at the use of a rotational shear interferometer to achieve compressive coherent sensing. So in these systems, we have a system where we're going to make a two-dimensional measurement, and we really have a pair of two-dimensional images that we would like to know. One is the stationary coherence function that describes the remote source, and one is a two-dimensional distribution that describes the exit pupil or the distortion, the isoplanatic distortion of the system. So in this paper, for example, one could measure the mutual intensity at the output of the system using a rotational shear interferometer, And then if one inverted that mutual intensity by taking its Fourier transform spatially under the Van Cittert-Zernike theorem, has shown it up all right. You see the distorted image shown here. But if one inverts instead with constrained optimization, where one tries to jointly estimate the distorting wavefront and the image with a sparsity constraint, in this case the lasso-based optimization strategy as shown here, one can recover both the wavefront distortion, which is shown at the lower right, and the image of the scene, which in this case is a very sparse scene, so this decompressive inference works well. So the point of this is just to point out again that the computational strategies and the measurement strategies we've discussed all come together in a wide variety of different options for analyzing these systems. Obviously, in this course, we're not going to go into extreme detail either in adaptive optics or imaging through turbulence, but it helps to be aware that the techniques that we've discussed are applicable to these systems. Now, the rotational shear interferometer is one method for measuring coherence. We've also talked in the last lecture about modal strategies for characterizing coherence. You can also use focal interferometry. So basically, rather than the two-beam interference that we've talked about with the rotational shear interferometer, we can think of a lens as a system that transforms the mutual coherence or any of the coherence functions. In the next chapter, we're going to discuss this in some detail when we talk about focal imaging systems for partially coherent and incoherent sources. But since we're talking here about characterizing the coherence function and seen through turbulence, it's helpful to see that you can make systems like this astigmatic coherence sensor, which uses a lens system with the adjustable astigmatism to characterize the full four-dimensional mutual coherence function. So in this case, there's a turbulent screen, in this case a distorting plastic plate. We're trying to see an image through that plate. If we image directly through the plate, you see a blurry, distorted image. But it turns out you can, in fact, measure the full multidimensional coherence function, the full cross-spectral density of the system. Here's an example from that system of the analytic field of the distortion as estimated after finding the mutual coherence function, the cross-spectral density, and then implementing a coherent mode decomposition on the cross-spectral density, assuming that there is a single brightest point source in the scene, and that brightest point source's wavefront would correspond to the distortion. You get this image of the distortion, and then you can apply that distortion to all of the modes to form a well-formed image of the scene through the turbulence. So this image may not look like much. It's a bunch of LEDs where we're looking at a simple source. This was U of I, because this work was done at the University of Illinois. But when you consider that this was the image without the distortion correcting, you can see that something very powerful was done here. So this concludes our basic introduction to coherence theory and coherence functions. It's time for us to talk about focal imaging systems, which we'll begin to discuss in episode 48. This is an example of what we're going to discuss in that episode, where, in the case of coherent systems and what we've done with coherence functions, the basic problem in a lot of optical systems is how do we propagate the input field to the output field? How do we build a forward model relationship between the input field and the output field? And we're going to start by talking about what if we know the cross-spectral density or the on the input plane, and we're going to transform that cross-spectral density with a lens and measure the irradiance in the focal volume. We need to discover what is the relationship between these distributions.